Hello everyone. Thanks for the huge support to our first video on general and ultraviolet spectroscopy and for the likes, the shares and the subscribes. As promised, we are back with the second video of the series titled Learning Spectroscopy with the help of question-answer method. In this video, we will study the second type of spectroscopy or the infrared spectroscopy following the same method of learning. I mean, interaction method or question-answer method. Let's start. The first question is, what is infrared spectroscopy? What is its other name? The answer to this question is very simple. Infrared spectroscopy is an analytical technique used to study the interaction of infrared radiation with matter. This technique is primarily used to identify and study different chemicals based on their molecular vibrations. In this technique or spectroscopy, we measure the absorption of infrared light by a sample to find out or reveal the molecular structure of the compounds. It is also known by another name. The other name for the infrared spectroscopy is vibrational spectroscopy, since it focuses on the molecular vibrations or transitions between different vibrational energy states of the same electronic energy state. The second question is, what is the principal difference between the ultraviolet spectroscopy and the infrared spectroscopy? The answer to this question is very simple. The principal difference between ultraviolet spectroscopy and the infrared spectroscopy lies in the energy of the electromagnetic radiation they use. Ultraviolet spectroscopy deals with electronic transitions, where molecules absorb ultraviolet light to promote electrons to higher energy levels. In this spectroscopy, the electrons undergo transition from their lower energy electronic state to their higher energy electronic state. Infrared spectroscopy deals with vibrational transitions, where molecules absorb infrared light, causing bonds within molecules to stretch or bend. In this spectroscopy, the electrons undergo transition from their lower energy vibrational state to their higher energy vibrational state. However, the electronic state corresponding to the lower and the higher energy states remain the same. Now we will move to the third question. Why is infrared spectroscopy better than ultraviolet spectroscopy? The answer to this question is very simple and easy. Infrared spectroscopy is better in certain cases because infrared spectroscopy provides detailed information about the functional groups present in a molecule, allowing for the identification of specific bond types. Infrared spectroscopy is non-destructive, unlike some ultraviolet methods. Infrared spectroscopy helps in studying a wider range of compounds, especially organic molecules. However, which out the two techniques is better depends on the context, as ultraviolet spectroscopy can be more suited for analyzing conjugated systems and electronic transitions. Now we will move to the fourth question. What is the range of the infrared region of the electromagnetic spectrum? Explain in terms of wavelength, frequency, wave number, and energy. The answer to this question is very simple. Wavelength from 0.78 micrometer to 1000 micrometer, from 780 nanometers to 1 millimeter. The infrared region is typically divided into three subregions: near infrared, from 0.78 micrometer to 2.5 micrometer, mid infrared, from 2.5 micrometer to 50 micrometer, and far infrared, from 50 micrometer to 1000 micrometer. Frequency 3.8 into 10 raised to power 13 Hz to 4.0 into 10 raised to power 14 Hz. Wave number from 10 cm inverse to 13,000 cm inverse. Energy from approximately 0.0012 electron volts to 1.5 electron volts. Now we will move to the fifth question. What are the commonly used units of infrared radiations while studying infrared spectroscopy? The answer to this question is very simple. The commonly used units in infrared spectroscopy include wavelength. We commonly use micrometers or nanometers as units. Wave number, centimeter inverse, the number of wave cycles in 1 centimeter, commonly used because it is directly proportional to energy. Frequency, Hz, Hertz. Energy, EV, electron volts. Now we will move to the sixth question. What are the different parts of the infrared region which is actually a part of the electromagnetic spectrum? The answer to this question is very simple. The infrared region is divided into three parts. Near infrared, from 0.78 micrometer to 2.5 micrometer. Mid-infrared, from 2.5 micrometer to 50 micrometer. This is the most commonly used region in infrared spectroscopy. Far infrared, from 50 micrometer to 1000 micrometer. Now we will move to the seventh question. What is the principle of infrared spectroscopy? Explain in detail. The answer to this question is very simple. The principle of infrared spectroscopy is based on the absorption of infrared radiation by molecules, which causes changes in the vibrational and rotational states of the chemical bonds. When infrared light passes through a sample, specific frequencies are absorbed by the molecules, which correspond to the vibrational frequencies of the bonds between atoms. This absorption leads to changes in the molecular dipole moment. The absorption pattern, often called an infrared spectrum, is unique to each molecule, creating a fingerprint that can be used to identify substances and analyze their structures. Next question is question number 8. Why is infrared spectroscopy also known as vibrational rotational spectroscopy? The answer to this question is very simple. Infrared spectroscopy is also called vibrational rotational spectroscopy because the absorption of infrared radiation induces transitions in both the vibrational and rotational energy levels of molecules. While infrared spectroscopy primarily focuses on vibrations, molecules also undergo rotational transitions simultaneously, especially in the gas phase. The next question is question number 9. What do you mean by infrared active transitions and infrared inactive transitions? The answer to this question is very simple. Infrared active transitions. These are those transitions in which a molecule absorbs infrared radiation, resulting in a change in its dipole moment. These transitions correspond to molecular vibrations that can be detected in an infrared spectrum. Infrared inactive transitions. These are those transitions that do not involve a change in the molecular dipole moment. As a result, these vibrational modes do not absorb infrared radiation and are invisible in the infrared spectrum. Now we will move to the 10th question. Why are some of the vibrational transitions infrared active and others are not? The answer to this question is very simple. Vibrational transitions are infrared active only if they result in a change in the dipole moment of the molecule. When molecules vibrate, their charge distribution changes. If this change in charge distribution leads to a fluctuating dipole moment, the vibration can interact with infrared light and absorb it. Vibrational modes like symmetric stretching often do not result in a dipole moment change, making them infrared inactive. Now we will move to the 11th question. What is dipole moment? Explain in detail. The answer to this question is very simple. A dipole moment is a measure of the separation of positive and negative electrical charges within a molecule. It quantifies the polarity of a molecule, which occurs when there is an unequal distribution of electrons between bonded atoms. Dipole moment is a vector quantity and is represented by the symbol mu, with both magnitude and direction. Magnitude, it is calculated as the product of the charge difference and the distance between the centers of positive and negative charges. Mu u is equal to Q times D or Q multiplied by D, where Q is the charge and D is the distance between the charges. Direction, the dipole moment points from the negative charge to the positive charge. In molecules with polar bonds, such as HCl, the dipole moment arises due to the electronegativity difference between hydrogen and chlorine, leading to a partial positive charge on hydrogen and a partial negative charge on chlorine. This creates a dipole moment. Dipole moment is crucial in infrared spectroscopy because only molecules with a changing dipole moment during vibration can absorb infrared radiation, making them infrared active. Now we will move to the 12th question. What do you mean by molecular vibrations? What are their types? Explain in detail. The answer to this question is very simple. Molecular vibrations refer to the periodic motions of atoms within a molecule, which occur as the atoms vibrate around their equilibrium positions. These vibrations can be induced by the absorption of energy, such as infrared radiation, which causes the atoms to oscillate. Molecules can undergo two types of vibrations. Stretching vibrations, these involve changes in the bond length between atoms. The atoms move along the bond axis, either pulling apart, extension, or moving closer together, compression. Stretching can be symmetric stretching, all atoms move in or out simultaneously. Asymmetric stretching, one atom moves in while the other moves out. Bending vibrations, these involve changes in the bond angle between atoms. Types of bending include in-plane bending, scissoring and rocking. Out-of-plane bending, wagging and twisting. Now we will move to the 13th question. What is meant by fundamental vibrations? Explain with reference to infrared spectroscopy. The answer to this question is very simple. Fundamental vibrations. Thus, vibrations refer to the basic vibrational modes of a molecule, where each mode corresponds to a distinct type of atomic movement within the molecule. In infrared spectroscopy, fundamental vibrations are the primary vibrations that arise from the normal oscillation of bonds when the molecule absorbs infrared light. For a molecule with N atoms, the number of fundamental vibrations can be calculated using the following formula. For linear molecules, the formula is 3n-5. For nonlinear molecules, the formula is 3n-6. For example, water, H2O, is a nonlinear molecule with 3 atoms, so it has 3 fundamental vibrational modes: symmetric stretching, asymmetric stretching, and bending. Now we will move to the 14th question. What are overtones? Explain with reference to infrared spectroscopy. The answer to this question is very simple. Overtones are vibrational transitions where the molecule absorbs energy that corresponds to a multiple of the fundamental vibrational frequency. In simpler terms, an overtone occurs when a molecule is excited to a higher vibrational level, for example, from the ground state to the second or third vibrational state, instead of just the first. In infrared spectroscopy, overtones appear at frequencies that are multiples of the fundamental vibration but are generally weaker in intensity. For instance, if a fundamental vibrational frequency occurs at 1000 centimeter inverse, its first overtone may appear around 2000 centimeter inverse. Now we will move to the 15th question. What two main types of fundamental vibrations do we observe in infrared spectroscopy? The answer to this question is very simple. The two main types of fundamental vibrations observed in infrared spectroscopy are stretching vibrations. These involve changes in the bond lengths between atoms. It can be symmetric or asymmetric. Bending vibrations. These involve changes in bond angles and can be further classified into scissoring, rocking, wagging, and twisting. Now we will move to the 16th question. What are stretching vibrations and what are their types? Explain in detail. The answer to this question is very simple. Stretching vibrations are vibrations where the bond length between atoms changes, meaning that the atoms move along the bond axis. There are two types of stretching vibrations. Symmetric stretching. In symmetric stretching, all the bonds elongate or compress simultaneously. For example, in a molecule like CO2, both oxygen atoms can move away from the carbon atom at the same time, or both can move towards it. Asymmetric stretching. In asymmetric stretching, one bond lengthens while the other shortens. Using CO2 again as an example, one oxygen atom may move towards the carbon while the other moves away. The next question is question number 17. What are bending vibrations or deformations? What are their types? Explain in detail. The answer to this question is very simple. Bending vibrations involve a change in the bond angle between atoms as opposed to the bond length. These vibrations can occur in different planes and directions. The four main types of bending vibrations are in-plane bending, scissoring. The two atoms move toward or away from each other in a fashion resembling the blades of scissors. Rocking. Both atoms move in the same direction, creating a rocking motion of the bonds in the plane of the molecule. Out-of-plane bending. Wagging. The atoms move up and down relative to the plane of the molecule, like a wagging tail. Twisting. The atoms move in opposite directions perpendicular to the molecular plane, creating a twisting motion. The next question is question number 18. What is Hooke's law? How is this law applicable in infrared spectroscopy? Explain in detail. The answer to this question is very simple. Hooke's law states that the force required to extend or compress a spring is proportional to the displacement of the spring from its equilibrium position. F is equal to minus K multiplied by X, where F is the force, K is the force constant related to the stiffness or the strength of the bond, and X is the displacement. In infrared spectroscopy, Hooke's law can be applied to approximate the vibrational frequency of a bond in a molecule. The bonds between atoms behave like springs, and their vibrational frequencies depend on the force constant of the bond and the masses of the bonded atoms. The frequency of vibration is given by nu is equal to 1 by 2 pi multiplied by whole square root of k divided by nu, where k is the force constant and mu is the reduced mass of the two atoms. The next question is question number 19. What is force constant? What is its analog in spectroscopy? Explain in detail. The answer to this question is very simple. The force constant, K, measures the strength or stiffness of a bond in a molecule. It quantifies how strongly atoms are bonded to each other. The higher the force constant, the stronger the bond, and the higher the vibrational frequency. In spectroscopy, the force constant is analogous to the stiffness of a spring in Hooke's law. In chemistry, it is equal to the stiffness or the strength of the bond. It is directly related to the vibrational frequency of a bond. Stiffer or stronger bonds with larger force constants require higher energy to vibrate, which means these will vibrate at higher frequencies, while weaker bonds will vibrate at lower frequencies as lesser amount of energy is required for their vibration. The next question is question number 20. What is the importance of force constant in infrared spectroscopy? Explain in detail. The answer to this question is very simple. The force constant is critical in infrared spectroscopy because it determines the vibrational frequency of a molecular bond. A higher force constant indicates a stronger bond, resulting in a higher vibrational frequency. This frequency, measured in terms of wave numbers, centimeter inverse, corresponds to specific absorption peaks in the infrared spectrum. By analyzing these absorption peaks, scientists can deduce information about the strength and nature of the bonds within a molecule. The force constant thus plays a vital role in helping identify functional groups and determine molecular structures. The next question is question number 21. What is center of mass and how is it calculated? Explain its importance. The answer to this question is very simple. The center of mass of a system is the point where the entire mass of the system can be considered to be concentrated for the purpose of analyzing motion. For a collection of particles, the center of mass is a weighted average of their positions based on their masses. For a two-particle system, the center of mass position, RCM, is calculated using RCM is equal to M1R1 plus M2R2 divided by M1 plus M2, where M1 and M2 are the masses of the particles. R1 and R2 are their positions. For a system with multiple particles, this generalizes to is equal to summation MIRI divided by summation MI, where MI and RI are the mass and position of the ith particle. Importance: the center of mass is crucial in physics because it simplifies the analysis of complex systems by reducing them to a single point. In mechanics, the motion of a system can often be described by tracking the motion of its center of mass, especially under the influence of external forces. In infrared spectroscopy, the center of mass helps in understanding molecular vibrations and rotations because molecules rotate and vibrate about their center of mass. The next question is question number 22. What is meant by reduced mass and how is it calculated? Explain its importance. The answer to this question is very simple. Reduced mass is a concept used to simplify the description of two-body systems, particularly when dealing with molecular vibrations and rotations. It is defined as the effective mass that accounts for the two bodies' relative motion. The reduced mass, mu/mu, for two masses m1 and m2 is calculated as mu is equal to m1 into m2 divided by m1 plus m2. Importance: reduced mass is essential in determining vibrational frequencies of diatomic molecules in infrared spectroscopy. The vibrational frequency of a bond depends on both the force constant of the bond and the reduced mass of the atoms. It simplifies the two-body problem into a single-body problem by allowing calculations as if there is only one body with mass mu. The next question is question number 23. Name and explain in detail the factors affecting position of band or absorption frequency in infrared spectroscopy. The answer to this question is very simple. The position of absorption bands or frequencies in infrared spectroscopy is affected by several factors. Bond strength, force constant. Stronger bonds, higher force constant, result in higher absorption frequencies. For instance, AC triple bond C absorbs at a higher frequency than ACC double bond. Mass of atoms: lighter atoms vibrate at higher frequencies than heavier atoms. For example, ACH bond will have a higher absorption frequency than ACD, deuterium, bond because hydrogen is lighter than deuterium. Bond length: shorter bonds generally have higher absorption frequencies because they are stiffer, which makes them vibrate faster. For instance, triple bonds, shorter, absorb at higher frequencies than double or single bonds. Hybridization of the bonded atom: bonds involving atoms with more s character, sp hybridized, absorb at higher frequencies compared to those with more p character, sp2 or sp3 hybridized. For example, sp hybridized C8 stretches occur at higher frequencies than sp2 or sp3 C8 stretches. Electronegative substituents: electronegative atoms like oxygen or fluorine, when attached to a molecule, can pull electron density towards themselves, increasing the bone's stiffness and thus the vibrational frequency. For example, ACF bond absorbs at a higher frequency than ACH bond. Hydrogen bonding: hydrogen bonding lowers the absorption frequency because it weakens the bond by increasing its bond length. For instance, an OH bond stretching involved in hydrogen bonding absorbs at a lower frequency than a free OH bond stretching. The next question is question number 24. What are the factors affecting the intensity of peaks in infrared spectroscopy? Explain in detail. The answer to this question is very simple. The intensity of absorption peaks in infrared spectroscopy depends on the following factors. Change in dipole moment: the more significant the change in dipole moment during a molecular vibration, the more intense the absorption peak. Vibrational modes that cause a larger dipole moment change absorb more strongly and produce higher peaks in the spectrum. Number of absorbing molecules: the higher the concentration of the absorbing molecules, the more intense the peak. According to Beer-Lambert's law, absorbance is directly proportional to the concentration of the sample. Molecular symmetry: symmetrical molecules tend to have weaker infrared absorption because they have fewer dipole moment changes during vibration, resulting in less intense peaks. In contrast, asymmetrical molecules with more significant dipole changes have stronger peaks. Bond polarizability: bonds between atoms of different electronegativities, for example, C double bond O, have stronger dipole moments and absorb more infrared radiation than bonds between atoms of similar electronegativities, for example, C single bond C, leading to more intense peaks. Bond length and bond strength. Bonds with higher bond strength, shorter bond lengths, tend to absorb more energy, contributing to more intense peaks. The next question is question number 25. What do you mean by degrees of freedom? What is the total number of degrees of freedom for a molecule? What are the main types of degrees of freedom? The answer to this question is very simple. Degrees of freedom refer to the independent ways in which a molecule can move. Each degree of freedom corresponds to a possible mode of motion, translational, rotational, or vibrational. The total number of degrees of freedom for a molecule with n atoms is 3n. Each atom has 3 degrees of freedom, movement along the x, y, and z axis. For a molecule, linear molecules, total degrees of freedom is equal to 3n5. Nonlinear molecules, total degrees of freedom is equal to 3n6. Main types: translational degrees of freedom, movement of the entire molecule in x, y, or z directions, 3 degrees of freedom. Rotational degrees of freedom, rotation of the molecule around its axis, 2 for linear molecules, 3 for nonlinear molecules. Vibrational degrees of freedom, internal vibrations of the atoms within the molecule, calculated by subtracting translational and rotational degrees of freedom from the total. Now we will move to question number 26. Explain translational degrees of freedom, rotational degrees of freedom, and vibrational degrees of freedom. The answer to this question is very simple. Translational degrees of freedom describe the molecule's ability to move in space along x, y, or z axis. All molecules, regardless of size, have 3 translational degrees of freedom. Rotational degrees of freedom refers to the molecule's ability to rotate about its axis. Linear molecules have 2 rotational degrees of freedom, since rotation about the bond axis doesn't count. Nonlinear molecules have 3 rotational degrees of freedom, rotation around all 3 axes. Vibrational degrees of freedom correspond to the various ways atoms within a molecule can vibrate relative to each other. For a nonlinear molecule, the number of vibrational degrees of freedom is 3n-6, and for a linear molecule, it is 3n-5. Now we will move to question number 27. How can we calculate vibrational degrees of freedom for a monoatomic, diatomic, linear polyatomic, and nonlinear polyatomic molecule? Explain with examples. The answer to this question is very simple. Monoatomic molecules. A monoatomic molecule, for example, AR, has no bonds and hence no vibrational degrees of freedom. Diatomic molecules. For a diatomic molecule, for example, H2O2, the number of vibrational degrees of freedom is 1. This corresponds to the stretching or compression of the bond. Linear polyatomic molecules. For a linear polyatomic molecule like CO2, with 3 atoms, the vibrational degrees of freedom are 3n-5 is equal to 3 into 3 minus 5 is equal to 4. So, CO2 has 4 vibrational degrees of freedom. Nonlinear polyatomic molecules. For a nonlinear polyatomic molecule like H2O, 3 atoms, the vibrational degrees of freedom are 3n minus 6 is equal to 3 multiplied by 3 minus 6 is equal to 3. So, H2O has 3 vibrational degrees of freedom. Now we will move to question number 28. What is the relationship between the number of bands in the infrared spectrum and vibrational degrees of freedom? The answer to this question is very simple. The number of bands in the infrared spectrum corresponds to the number of different vibrational modes of the molecule. Each vibrational degree of freedom represents a unique mode of vibration, which typically results in one absorption band in the spectrum. However, not all vibrational modes are infrared active, i.e., detectable in the spectrum, so the number of observed bands may be fewer than the total vibrational degrees of freedom. Now we will move to question number 29. Do we always get the same number of bands in the infrared spectrum as shown by vibrational degrees of freedom? The answer to this question is very simple. No, we do not always get the same number of bands as the vibrational degrees of freedom because not all vibrations lead to infrared absorption. Only those vibrations that cause a change in the dipole moment of the molecule will appear as absorption bands in the infrared spectrum, infrared active vibrations. Vibrations that do not change the dipole moment are infrared inactive and do not produce bands. Now, we will move to question number 30. Why do we not get the same number of bands in infrared spectroscopy as given by vibrational degrees of freedom? The answer to this question is very simple. We do not always get the same number of bands in infrared spectroscopy as indicated by vibrational degrees of freedom due to the following reasons. Infrared inactivity. Some vibrational modes do not cause a change in the dipole moment and are therefore infrared inactive. Degeneracy. In some cases, different vibrational modes may have the same energy, leading to overlapping bands or degenerate vibrations. Overtones and combination bands. Some observed bands are due to overtones, multiples of a fundamental frequency, or combination bands, resulting from the combination of two or more fundamental vibrations. Selection rules. Quantum mechanical selection rules may prevent certain transitions from being observed in the infrared spectrum. Now we will move to question number 31. What do you mean by combination bands in infrared spectroscopy? The answer to this question is very simple. In infrared spectroscopy, combination bands occur when two or more fundamental vibrational modes are excited simultaneously, resulting in the absorption of radiation at a frequency that is the sum of the frequencies of the individual vibrations. These bands are typically weaker than fundamental absorption bands and are seen in more complex molecules where multiple vibrational modes can interact. For example, if a molecule has two vibrational modes with frequencies nu1 and nu2, a combination band may appear at a frequency nu1 plus nu2. These bands provide additional information about the molecular structure and vibrational coupling. Now we will move to question number 32. What do you mean by difference bands in infrared spectroscopy? The answer to this question is very simple. Difference bands in infrared spectroscopy arise when the molecule absorbs radiation corresponding to the difference between two vibrational frequencies. Instead of adding the frequencies, as in combination bands, the difference between two vibrational modes creates a new band. The frequency of the difference band is expressed as nu1 minus nu2, where nu1 and nu2 are the frequencies of the individual vibrational modes. Difference bands are relatively rare and generally weaker than fundamental or combination bands. They typically occur in more complex vibrational systems where two or more modes interact. Now we will move to question number 33. What is meant by Fermi resonance? The answer to this question is very simple. Fermi resonance is a phenomenon in infrared spectroscopy where two vibrational modes that have similar energies, frequencies, interact and shift their absorption frequencies. This interaction can lead to the splitting of a single absorption band into two distinct bands of higher intensity. Fermi resonance occurs when a fundamental vibrational mode interacts with an overtone or a combination band that has a similar energy. The result is the appearance of two closely spaced bands in the infrared spectrum instead of one. This is important because it can provide insight into the structure and vibrational behavior of molecules. Now we will move to question number 34. What are the selection rules in infrared spectroscopy? Explain in detail. The answer to this question is very simple. Selection rules in infrared spectroscopy determine which vibrational transitions are allowed or forbidden based on changes in molecular dipole moment and symmetry. These rules are derived from quantum mechanics and help predict whether a particular vibrational mode will absorb infrared radiation. The primary selection rule for infrared activity is change in dipole moment. A vibrational mode is infrared active if it causes a change in the dipole moment of the molecule. Only vibrations that alter the distribution of charge in the molecule will interact with the infrared radiation and lead to absorption. For example, stretching vibrations in polar bonds like C double bond O or OH are infrared active because they cause dipole moment changes. In contrast, symmetrical molecules, for example, O2 or N2, may have vibrational modes that do not change the dipole moment, and thus these vibrations are infrared inactive. Now we will move to question number 35. What are the factors that affect the vibrational frequencies or position of bands in infrared spectroscopy? The answer to this question is very simple. Several factors affect the vibrational frequencies or the position of bands in infrared spectroscopy. Bond strength, force constant. Stronger bonds vibrate at higher frequencies, so the position of the absorption band shifts to higher wave numbers. Triple bonds, C triple bond C, absorb at higher frequencies than double, C double bond C, or single bonds, C single bond C. Mass of the atoms, heavier atoms vibrate more slowly, resulting in lower absorption frequencies. For example, CD bonds absorb at lower frequencies than C single bond H because deuterium is heavier than hydrogen. Bond length, shorter bonds are stiffer and absorb at higher frequencies compared to longer bonds. For example, C triple bond C bonds have shorter lengths and absorb at higher frequencies than C double bond C. Electronegativity. The presence of highly electronegative atoms can increase bond stiffness, leading to higher vibrational frequencies. For instance, CF bonds absorb at higher frequencies than CH bonds. Hybridization. Bonds involving sp hybridase atoms absorb at higher frequencies than those involving sp2 or sp3 atoms. This is because sp hybridase bonds have more SSS character, making them stronger. Resonance. Resonance delocalization of electrons can reduce bond strength and shift the absorption band to lower frequencies. Hydrogen bonding. Hydrogen bonding weakens the bond, causing a redshift, lower frequency, in the absorption band. For example, OH stretching in hydrogen-bonded alcohols occurs at a lower frequency than stretching in the free OH groups. Now we will move to question number 36. What is vibrational coupling? How does it affect the position of bands or absorption frequency in infrared spectroscopy? Explain with the help of examples. The answer to this question is very simple. Vibrational coupling occurs when two or more vibrational modes of a molecule interact with each other, resulting in shifts in the absorption frequencies. This happens when the vibrations of nearby bonds are not completely independent and affect each other due to their proximity or shared atoms. Factors that influence vibrational coupling. Proximity of bonded atoms, vibrations of two bonds involving a shared atom, for example, CH and CC bonds in CH2, can couple, leading to shifts in their absorption frequencies. Symmetry. Symmetrical molecules may exhibit coupled vibrational modes where the atoms vibrate in phase or out of phase, leading to distinct absorption peaks. Example, in the case of ethylene, C2H4, the CH stretching vibrations in the CH2 groups can couple, leading to the appearance of symmetric and asymmetric stretching modes. The symmetric mode absorbs at a lower frequency than the asymmetric one. Now we will move to question number 37. How does hydrogen bonding affect the position of bands or absorption frequency in infrared spectroscopy? Explain with the help of examples. The answer to this question is very simple. Hydrogen bonding can have a significant impact on the position of absorption bands in infrared spectroscopy by lowering the frequency at which the bond absorbs infrared radiation. Hydrogen bonds weaken the covalent bonds involved in the interaction, resulting in a redshift, lower frequency, of the associated absorption band. Examples. In alcohols, ROH, the OH stretching vibration typically occurs around 3600 cm inverse for free O groups. However, when hydrogen bonding occurs, for example, in water or in concentrated alcohols, the OH absorption shifts to a lower frequency around 3200 to 3500 cm inverse. Similarly, in carboxylic acids, RCOOH, the OH stretch also shifts to a lower frequency due to strong hydrogen bonding in the dimer form of the acid. Now we will move to question number 38. What is inductive effect and what are its types? The answer to this question is very simple. The inductive effect refers to the electron withdrawing or electron donating influence of substituents on a molecule through sigma bonds. It affects the electron density along the molecular framework, influencing properties such as bond polarity and reactivity. There are two types of inductive effects. Plus I effect. Electron donating inductive effect substituents that donate electron density through sigma bonds. Alkyl groups, for example, CH3, methyl, C2H5, ethyl, exhibit the plus I effect by pushing electron density toward the rest of the molecule. Minus I effect. Electron withdrawing inductive effect substituents that withdraw electron density through sigma bonds. Electronegative atoms or groups, for example, F, Cl, NO2, exhibit the minus I effect by pulling electron density away from the molecule, making the bond more polar. Now we will move to question number 39. How does the position of absorption band in infrared spectrum change with plus I and minus I effect? The answer to this question is very simple. Plus I effect. Electron donating groups increase electron density around the bonded atoms, weakening the bond and shifting the absorption band to lower frequencies, redshift. For example, alkyl groups attach to AC double bond or reduce its strength, causing the carbonyl stretch to appear at a lower frequency. -I effect. Electron withdrawing groups reduce electron density around the bonded atoms, strengthening the bond and shifting the absorption band to higher frequencies, blue shift. For example, a nitro group, NO2, attached to AC double bond O strengthens it, causing the carbonyl stretch to absorb at a higher frequency. The next question is question number 40. What is resonance effect? What are its types? The answer to this question is very simple. The resonance effect refers to the delocalization of electrons within a molecule due to conjugation between p orbitals. This effect stabilizes the molecule and influences its electronic and structural properties. Resonance can either enhance or reduce the strength of specific bonds. There are two types of resonance effects. Pulsar effect, electron-donating resonance groups that donate electron density via resonance, increasing electron density in a conjugated system. For example, O and O groups exhibit the pulsar effect by donating electrons through resonance into the aromatic ring or double bonds. -R effect, electron withdrawing resonance groups that withdraw electron density via resonance, decreasing electron density in a conjugated system. For example, NO2, nitro, and CN groups exhibit the -R effect by pulling electrons away through resonance. The next question is question number 41. How does the position of absorption band in infrared spectrum change with +R and R effect? The answer to this question is very simple. +R effect, electron-donating groups increase electron density in the conjugated system, weakening bonds and shifting absorption bands to lower frequencies, red shift. For example, an OH group attached to an aromatic ring weakens the C double bond O in conjugation, causing the carbonyl stretch to appear at a lower frequency. -R effect, electron withdrawing groups decrease electron density in the conjugated system, strengthening bonds and shifting absorption bands to higher frequencies, blue shift. For example, a nitro group, NO2, attached to an aromatic ring strengthens the C double bond O, shifting the carbonyl stretch to a higher frequency. The next question is question number 42. How is infrared spectrum recorded? What is the instrument used for recording infrared spectrum called? The answer to this question is very simple. The infrared spectrum of a molecule is recorded using an instrument called an infrared spectrometer. This process involves passing infrared radiation through a sample and measuring the amount of radiation absorbed at different wavelengths. The detector measures the intensity of the transmitted light, and the resulting absorption spectrum is plotted as a function of frequency or wavelength, showing absorption peaks that correspond to different vibrational modes of the molecules. The instrument used for this purpose is called an infrared spectrometer. It can be either a dispersive spectrometer, where a prism or grating separates the infrared radiation into different wavelengths, or a Fourier transform infrared (FTIR) spectrometer, which uses an interferometer to collect the entire spectrum simultaneously and processes it using Fourier transformation. The next question is question number 43. What are the main components of infrared spectrometer? Explain in detail. The answer to this question is very simple. The main components of an infrared spectrometer are: radiation source, provides infrared radiation. Common sources include Nernst-Glaser, a heated filament that emits infrared radiation. Global source, a silicon carbide rod heated electrically to emit infrared radiation. Monochromator, for dispersive spectrometers, this component selects specific wavelengths of infrared radiation using a prism or grating and directs them toward the sample. FT infrared spectrometers do not use monochromators but employ an interferometer instead. Sample holder holds the sample in place for the infrared radiation to pass through. The sample can be in solid, liquid, or gaseous form, and various sampling techniques are used depending on the sample's state. Detector measures the intensity of the transmitted infrared radiation. Common detectors include thermocouples, detect changes in temperature due to infrared absorption. Bolometers measure changes in resistance due to absorbed infrared radiation. Pyroelectric detectors use materials like lithium tantalate, which generate a charge when heated by infrared radiation. Data processor, computer collects and processes the signal, converting it into an absorbance or transmittance spectrum. In FT infrared spectrometers, the interferogram is converted into a spectrum using a mathematical process called Fourier transform. The next question is question number 44. What are the different sampling techniques used in infrared spectroscopy? Explain in detail. The answer to this question is very simple. Different sampling techniques are used depending on the physical state of the sample. Solid samples. KBr pellets. The sample is finely ground and mixed with potassium bromide, KBr, then pressed into a transparent pellet that can be placed in the infrared beam. Mull technique. The sample is mixed with a mulling agent like nujol, mineral oil, to form a paste, which is then smeared between salt plates. Attenuated total reflectance, AT, are a solid sample is placed in contact with an ATR crystal and the infrared beam reflects internally. This technique is widely used in modern FT infrared instruments. Liquid samples. Thin film method. A thin layer of liquid sample is sandwiched between two infrared transparent salt plates such as NaCl or KBr. Solution method. The sample is dissolved in an infrared transparent solvent and placed in a liquid cell with windows made of salt crystals. Gas samples. Gaseous samples are analyzed by placing them in a long path gas cell with infrared transparent windows. Attenuated total reflectance, ATR, can be used for solids, liquids, or gels. It eliminates the need for special sample preparation. The next question is question number 45. Name the solvents that are commonly used for preparing the sample for recording the infrared spectrum. The answer to this question is very simple. The solvents used in infrared spectroscopy must not absorb in the infrared region of interest. Common solvents include carbon tetrachloride, CCl4, chloroform, CHCl3, carbon disulfide, CS2, hexane, C6H14, cyclohexane, C6H12. The next question is question number 46. What are points that you must keep in mind for choosing the solvent for making a sample for recording infrared spectrum? The answer to this question is very simple. When choosing a solvent for infrared spectroscopy, keep the following points in mind. Infrared transparency. The solvent must not have significant absorption in the region where the sample absorbs. Solvents like water and alcohols are avoided because they strongly absorb in the infrared region. Solubility. The sample must be soluble in the chosen solvent at the desired concentration. Chemical inertness: the solvent should not react with the sample or degrade during the measurement. Boiling point: for liquid samples, a solvent with an appropriate boiling point ensures that it doesn't evaporate too quickly during measurement. The next question is question number 47. What are the different parts of infrared spectrum? The answer to this question is very simple. The infrared spectrum is generally divided into two main regions. Fundamental group region, from 4000 cm inverse to 1500 cm inverse. This region contains characteristic absorption bands for functional groups like OH, C double bond O, NH, etc. Fingerprint region, from 1500 cm inverse to 400 cm inverse. This region contains complex absorption patterns due to molecular vibrations involving the entire structure. The pattern is unique to each compound, making it useful for identification. The next question is question number 48. Explain fundamental group region of infrared spectrum in detail with the help of some examples. The answer to this question is very simple. The fundamental group region, 4000 to 1500 cm inverse, is where the vibrations of common functional groups occur. This region provides information about the presence of specific bonds within a molecule. Each functional group absorbs at characteristic frequencies, making this region useful for qualitative analysis. Examples: O single bond H stretching, broad absorption around 3200 cm inverse to 3600 cm inverse for alcohols and carboxylic acids. C double bond O stretching, strong sharp absorption is around 1700 cm inverse for carbonyl compounds like ketones, aldehydes, and esters. N single bond H stretching, absorption is around 3300 cm inverse for amines. The next question is question number 49. Explain fingerprint region of infrared spectrum in detail. The answer to this question is very simple. The fingerprint region, from 1500 cm inverse to 400 cm inverse, contains complex and unique absorption patterns due to a combination of bending, stretching, and other vibrational modes of the entire molecule. This region is highly specific to each compound, even for molecules that have the same functional groups but differ in structure. As a result, it is used to confirm the identity of a compound by comparing its spectrum to known standards. The next question is question number 50. What are the limitations of infrared spectrum? The answer to this question is very simple. While infrared spectroscopy is a powerful tool, it has certain limitations. Low sensitivity: it is less sensitive compared to other techniques like mass spectrometry or NMR for detecting small amounts of a sample. Complex spectra: the spectra can be complex, especially in the fingerprint region, making interpretation difficult without comparison to reference spectra. Weak absorptions: some molecules or functional groups may not produce strong infrared absorption, particularly nonpolar bonds. Interference from water and CO2: infrared spectra can be affected by atmospheric water vapor and carbon dioxide, leading to additional peaks. The next question is question number 51. What are the different types of peaks observed in infrared spectrum? The answer to this question is very simple. Different types of peaks in infrared spectra correspond to different vibrational modes. Sharp peaks: these indicate strong, well-defined absorptions, often associated with stretching vibrations, for example, C double bond O, C single bond H. Broad peaks. These occur due to hydrogen bonding, such as OH stretching in alcohols and carboxylic acids. Weak peaks result from weaker absorption or infrared active vibrational modes that have low intensity. The next question is question number 52. How is infrared spectroscopy used for determining the molecular structure? Explain in detail. The answer to this question is very simple. Infrared spectroscopy is used to identify functional groups within a molecule based on their characteristic absorption frequencies. By analyzing the absorption peaks in the spectrum, the types of bonds present, C double bond O, O single bond H, N single bond H, etc., and their environments can be determined. This helps in deducing the molecular structure, confirming known structures, or distinguishing between isomers. The next question is question number 53. How is infrared spectroscopy used for studying the progress of a reaction? Explain in detail. The answer to this question is very simple. Infrared spectroscopy can be used to monitor the disappearance of reactants and the formation of products during a chemical reaction. By measuring changes in the intensity or position of specific absorption bands over time, the progress of the reaction can be tracked. For example, the decrease of AC double bond O stretch in a carbonyl compound and the appearance of new peaks can indicate the transformation of a reactant into a product. The next question is question number 54. How is infrared spectroscopy used for differentiating between different compounds? Explain in detail. The answer to this question is very simple. Each compound has a unique infrared spectrum, especially in the fingerprint region. Infrared spectroscopy can differentiate between different compounds by comparing their spectra. Differences in the position, intensity, and shape of absorption bands for functional groups allow chemists to distinguish between compounds with similar structures or isomers. The next question is question number 55. How is infrared spectroscopy used for finding the type of hydrogen bonding? Explain in detail. The answer to this question is very simple. Hydrogen bonding affects the position and shape of O single bond H, N single bond H, and similar stretching vibrations. Strong hydrogen bonding typically shifts the absorption band to lower frequencies, redshift, and broadens the peak. By analyzing the shape and position of these peaks, the presence and strength of hydrogen bonding can be inferred. For example, the OH stretch in alcohols appears as a broad peak around 3200 cm inverse to 3600 cm inverse due to hydrogen bonding. The next question is question number 56. How is infrared spectroscopy used for studying the purity of a compound? Explain in detail. The answer to this question is very simple. A pure compound produces a characteristic and reproducible infrared spectrum. Any impurities in the sample would introduce additional peaks or modify existing ones. By comparing the infrared spectrum of a sample to that of a pure reference compound, the presence of impurities can be detected based on unexpected absorption bands or changes in peak intensity. I hope this video will help you in learning the infrared spectroscopy in easy and simple way without much efforts. If you enjoyed and liked the video and also wish to have such informative and interesting videos, please like, share and subscribe. Your feedback is the only key to our improvement. Please point out anything you want or should be added in the next videos in the comment box. Thanks. And we will meet soon, most likely tomorrow, with another similar video on NMR spectroscopy.